So I mentioned at the end of the last example that if you take the derivative as a function, it's no longer equal to the slope, but it's something that gives you slope. Okay, and that's we're going to clarify what that means now. So in the previous example, let's just summarize what we had. Right, we had our function f is given by f of x is equal to x cubed, and we calculated through quite a bit of work that the derivative f prime of x is given by 3x squared. That's what we calculated in the previous example. Now let's look at what that really means. How do you interpret that? Well, let's draw a sketch of the graph of f. So it's a cubic, right? It's a cubic y equals x cubed. So what is that going to look like? It goes through the origin, and it looks something like this. Okay, so something like that anyway. So let's say we take a couple of points. How about 1, and then call that -2, and then we got the origin as well, right? So we can draw a corresponding point on the curve for each of those x values, and we can sketch the tangent line. Just to keep this picture from getting too messy, I'm going to use a ruler here. If I draw the tangent line here, it's going to look something like that, right? And there's also, I can draw the tangent line at the point x equals 1 here, and I get a tangent line here as well. Right, and then at the point x equals 0, right at the origin, I can draw a tangent line there. It's going to maybe, actually, yeah, I'll try and draw it just a bit above so it doesn't coincide too much with the x-axis. You can kind of see a black tangent line going along here, right? Right to be tangent to the curve right at this point. So what are the slopes of all those lines? Well, the derivative as a function is going to tell you. All you have to do is tell it the x value, right? So, for example, if I want the slope of this tangent line here that's in green, well, it's tangent to the curve at this point, which has an x value of 2. So if I plug in, or pardon me, -2. So if I plug -2 into f prime, I get f prime of -2 is 3 times -2 squared, which is equal to 12. And that is going to be the slope of that line, right? The 12 is going to be the slope of this green line. What about the red tangent line here? It had its tangent to the curve at this point, which has an x coordinate of 1. So if I work out f prime of 1, I'm going to get 3 times 1 squared, right? Plug 1 into f prime. I get 3 times 1 squared. I'm going to get 3. So that is the slope of this line. And what about the slope of the black line? And it's almost hard to see. I'm going to shade that a bit darker because that's unfortunate when the line is right over top of the x-axis. It just blurs together and you can't really see. So let me just shade this a little bit more strongly so you can really see that line stand out. That black line, what's the slope of that black tangent line? Well, it's tangent to the graph of y equals x cubed at the origin, which has an x coordinate of 0. So if you want its slope, well, and it's a flat line, right? So right off the bat, you know its slope is going to be 0. If this tool is any good, if it's worth anything at all, it better give you 0 as the slope, and in fact it will, right? Because if you plug in the x coordinate of 0, because that's the x coordinate of the origin, the point at which this line is tangent to the curve, you're going to get 0, because you plug in 0 to f prime, you're going to get 3 times 0 squared, which is equal to 0. Right, so you see how we can very quickly get the slope of many different lines once we have the derivative as a function. If you were to just use the derivative as a point, this original definition, we could have computed f prime of -2 using this limit definition. Then we could have computed f prime of 0 using this limit definition. And then we could have computed f prime of 1 using this limit definition. And that would be the same as computing the slopes of each of these 3 lines. one at a time, and that would involve 3 limit calculations that all might be lengthy on their own, right? So it's sometimes better, in fact it's usually better, to just compute the derivative as a function once, right? This actually wouldn't have been any easier to just do the derivative at one point than it was to do all this. So it's definitely worth taking the derivative as a function. Then once you have this rule, you want the slope at another point, just plug it into here. And that's plugging a point into here is a lot easier than doing all this work, right? I hope you're convinced of that. So that's the power of the derivative as a function. So this remark just sums it up again. So the derivative as a function gives us the slope of every tangent line at once, all bundled up into a rule, right, into a formula. That's the power of the derivative as a function. So it's a useful tool. I'll just do this because I like to do it when I remember to. Okay, also note something about this function, this cubic function here. As you move to the right, the function always seems to be going up, right? It's always going up. And actually, the reason for that is because its derivative is always positive, or at least it's never negative, right? This derivative is never negative because it's x. If you plug in any value, you're going to square it and multiply it by the positive number 3. So the result is never going to be negative. It can be 0 only at the point 0, but at every other point, the derivative is positive, right? So you notice as you move to the right, the function is increasing, always. So that should be the thought in the back of your mind when we read this fact here. So let I be an open interval. So we're going to start with some open interval of points. You might think of it as, say, the -2 to 0. This would be an example of an open interval that you should think of for this. If you have a function whose derivative is positive at every point in that interval, then your function is going to be increasing on that interval. So for example, the function its derivative is positive everywhere except at the point 0. So the open interval -2 to 0, for example, then f prime of x is going to be positive on that open interval. So that means the function's increasing on that interval, and certainly it is. If you look at the picture, you can see that. Okay, and then the second remark, that's just an example, but the second remark says the opposite. If it so happens that on your open interval, f prime of x is negative at every single point in that interval, then the original function f is decreasing on that interval. That's something that we're going to look more in detail at later in the course. We won't worry about, that's not going to be used too much right now, but when we get into chapter 4 and we get into optimization and then curve behavior and curve sketching, that's when we're really going to use this fact a lot. So I just wanted to introduce it early for now, but we will talk more about this as we get underway. Okay. The rest of the stuff on this page that we'll spend a few minutes going through is mostly just going to be about notation now. We're going to discuss higher derivatives, but actually this part down from here to here is just going to be notation. We'll talk about higher derivatives on the next page. So remember that we don't always write functions in functional notation. Sometimes we just like to use output variables. Like we might like to use the letter y as an output variable and the letter x as an input variable. We can write functions that way too, and sometimes you'll do that. So you can also write notation for derivatives with that in mind as well. Like for example, let's say we write y is equal to f of x. Okay, well if y is equal to f of x, then another way that I can write f prime of x is I can write this structure here, which almost looks like a fraction, but it's not. If you were to read it out loud, you would read it out loud as dy dx. Right, and it looks like a fraction dy over dx, and that's how it's written. And the way you would read it out loud formally is you would say the derivative of y with respect to x. Okay, so let me add that in. The derivative of y with respect to x. And a more of a casual way to think about it is just, it's the derivative of the function y. Oh, and by the way, x is the variable that y is defined in. That's another way to think about this, just to give yourself a way to wrap your head around it. For example, let's look at an example. Like, remember in the previous example we had f of x is equal to x cubed, and f prime of x was equal to 3x squared. Well, if we had written it differently and written the function x cubed in this fashion, like not written it in functional notation, but just written it as y as a function of x, like y is equal to x cubed, it's the same function, just written differently. So if we had written that, then we would have said, we could have said then dy dx is equal to 3x squared. So dy dx is just another way to say f prime of x. It's just another way to write down the derivative as a function. Okay, so that's just giving you an example of using this relationship. Let's summarize. There's actually other ways to write this as well, which I want to list for you now. I'm going to write all the different ways we can write it, and then give you some, because some of these actually have names that are standard too. So let's say if we had y is equal to f of x, then you have the following. There's a few different ways I can write it. I can just write y prime, so just write an apostrophe beside y. So it's not y to the power of 1, because that would just be the same as y. What this is, you should read this as y and then just a little apostrophe up at the side. It just stands for y prime. And that's actually how you would read it out loud, as y prime. It just means the derivative of y. So I can also write f prime of x. Right? We've seen that notation lots. You can also write dy dx. Right, as we just mentioned up here in this example. And you can also use operator notation, which you can sometimes, it looks similar, but you'll see the difference. But you see similarities between these two, right? dy dx means take the derivative of y with respect to x. That's how you would read this out loud formally. Over here, take the derivative with respect to x of y. They're not really any, they don't have any different meaning, but sometimes this notation is just much more convenient. This is called operator notation, because you're really describing, take the derivative with respect to x, you're kind of breaking that part off as just the operation that you're actually doing, and then you put the function inside with square brackets. Although you don't really have to use square brackets, but I typically will. And I think usually I see square brackets used with this notation, but I don't think that's strictly necessary, but I always use it. And then you can also write d dx and then write the f of x in the square brackets, right? It's just another way to write the same thing. Like if y is equal to f of x, then certainly these two notations ought to mean the same thing, right? So that's just a bunch of different ways you can write the same thing. These are called operator notation. Okay, and then this is called Leibniz notation. Okay, and then we can call these, you can call, I don't really want to write it down because it's not, I don't know if it's standard to call this prime notation, but that's what I'll, if I ever do have a need to refer to it out loud, I'll just call it prime notation. But what it's called is not so much important as how you make sure you use it correctly. Okay, so that is just a summary of all the different ways you can write the derivative of a function. And now on the next page, we'll talk about the higher order derivatives, like I promised you. So basically what happens if you take the derivative, well, as a function, the result is a function. What if you take the derivative of that? Right? That's the question that leads into the next page, and that's really what higher order derivatives are about.